My field of study, in fact, has been psychology for many years. I have been interested in the question of minds, where they come from, how they work. And this, many years ago, led me into the field of artificial intelligence because it seemed important to me to try to find languages rich enough to describe human mental life. And it has seemed to me that work in artificial intelligence has been a prime source for developing languages, developing conceptual systems within which we can express theories of mind and how the mind works. Just in order to put things in a little perspective here, I thought I would start out by saying a little bit about, this isn't going to be very visible, I'm afraid. Good. A little bit about my understanding of the nature of artificial intelligence and about how it relates to the kind of work that I'm going to talk about. At the beginning, I divide artificial intelligence up into roughly 3 categories. Theoretical artificial intelligence, experimental AI, and applied AI. And let me just I take the center core of artificial intelligence to be theoretical artificial intelligence, which I take to be the development of procedures or algorithms which are inspired by considerations of biological or most especially human information processing. Now, if that's where you start, then you can see that I take experimental AI to be the exploration of such procedures or algorithms through computer implementation. And finally, I take applied AI to be the application of such procedures / algorithms to various practical problems. Now, if you start out where I do, that is with this sort of a view, you can see that a field such as theoretical psychology, which is a field where I see myself fitting, is the application of such procedures or algorithms for stating theories of animal, especially human, information processing. And just to go another step, I would say that theoretical neurobiology, for example, is in part at least the application of such procedures, algorithms, etc., for stating theories of neural information processing. Now, the work that I do then, really, I take it to fall into all of these different categories, or at least, yes, really all of them. I see myself developing various kinds of algorithms and procedures inspired by consideration of human and animal intelligence. I see myself exploring those procedures through experimental computer simulation methodology. I see sometimes these procedures get applied to practical problems. I see myself, though, mostly trying to specify theories of human mind, of human intelligence, and of late trying to characterize also the nature of the relationship between mind and brain, in particular what might be called some aspects of theoretical neurobiology. Now, this pattern of relationships between psychology and artificial intelligence is fairly old. It goes back probably to the beginning of AI. The relationship between neurobiology and artificial intelligence, as was mentioned, also goes back to the beginning of AI. In early times, people tried to build computers which were based on considerations of how brains might function. In the 1950s, there was a fair amount of activity along this line, as well as along the more traditional symbol processing line. This work continued up into the 1960s, but starting in the mid-1960s probably, and increasing certainly through the 70s and even into the 80s, The line of considering what I call brain-style computation, or computational systems modeled on the way brains might work, that line of work began to diminish. And in place, there became the symbol processing paradigm that we're more or less all familiar with in artificial intelligence and computer science in general. Now, my work during the 1970s was largely in the symbol processing area. I was interested in building models of language understanding, in building models of memory, in building models of the storage and retrieval of information, and so on. And I found the tools of artificial intelligence to be useful. However, there were a number of things that I found rather frustrating among these tools. And in particular, among these things were considerations of how can I do cooperative computation. It's self-evident, I believe, that brains, human beings, function not by having sort of a sequence of steps of computation that they go through, at least for many tasks that they do, but rather certainly in the perceptual system, and I think also in the cognitive system as a whole, what we see instead, I believe, is something more the product of the cooperation of many, many processing elements. Now, I spent a good number of years trying to develop formalisms, languages within the context of artificial intelligence and symbolic processing, which I thought would be a good basis for developing theories of cooperative computation. Among the pieces of work that inspired me along these lines are the work, for example, some of you may know of, in the mid-70s by Raj Reddy at Carnegie Mellon University, development of the so-called hearsay model of speech perception, which was a model that was designed to work via cooperative computation of many specialized knowledge sources. However, for a variety of reasons, I found this general approach insufficient. And I decided, a number of us decided, in the around 1980 really, to begin exploring some alternatives, to go back to some of the earlier work that had been done, and to say, let's take seriously the notion that let's say a brain is a computer of some sort, and ask the question, what sort of computer is it? What's it made out of? What kind of programs run on this sort of a computer? What kind of programs run efficiently on this sort of computer? The issue of computer architecture is as any of you who know who have tried to write efficient computer programs, you have to take into account the nature of the machine on which the program is running. By that I mean, we know that some kinds of machines will do certain things. Some things are built into the hardware. Those things they do very efficiently. Other things they do less efficiently. Now, this is true even within the realm of so-called von Neumann machines, the conventional CPU-oriented machines with memory and stored program and so on. If we begin to think about more radical kinds of architectures, where there is no difference, for example, between processor and memory, they're intertwined. Knowledge is stored in the processing elements, and the processing is done by the memory. This is the kind of system that I believe brains are. And when we begin to think of architectures like that, it turns out that there are a number of important additional considerations as to what kind of algorithms brains might really be using when, say, they understand language, or when they retrieve information from memory, or store information in memory. To do this, then, I found myself more and more studying in the fields of neurobiology and computational, sort of analog computational systems, rather than our more conventional digital symbol processing universal computers. Now, so what we tried to do was say, if the brain is a computer, what kind of computer is it? And once we characterize that, what kind of information processing tasks are easily and naturally carried out on that kind of a computer? Once we make those steps, then we'll try to back away from brains per se and look at the more abstract character of this kind of a computational system and see what's it good for. How can it help us, say, in AI, or understanding minds, or understanding brains? So this is the kind of tack that I tried to take. Now at the beginning then, what we really imagine, or what we tried to do, and what was done in the early work in this area, is to begin with a level of analysis that we took as neurally inspired. That is to say, the computational elements of this kind of a model are going to be things about like neurons, about as complicated as a neuron, with roughly the same computational characteristics as neurons. So what are those? Well, we don't know exactly. Neurons are rather complex entities. They have some 20% of the energy that your body burns is burned in the brain to keep the very small percentage of your body going and functioning. So they're rather complex devices and energy consumptive. But we assume very simple models of the neuron in our work. For example, we usually use things like circles to designate what I call units in the more abstract way. They're model neurons. Call them units, processing units. And there's a limited kind of ways in which processing units work. Essentially, they get input from other processing units, and that works via connections. That is to say, direct wires, if you will, axons and dendrites in the brain, which carry the results of one neuron's computation, or one unit's computation, to another. To a first approximation, we can imagine that units do very simple computational work. In particular, what they do is accumulate in some way the output of their neighbors, accumulate in that some way, and the way in which we imagine that they accumulate it, and this is obviously an oversimplification, is to simply take the weighted sum of the outputs of the neighbors, as I have here, and that's more or less the input into the system. It's one number. And what the unit gets to do is decide what to say based on that number. But it has to make its decision in a very simple way. Essentially what it gets to do is send out a number, a single number. And the way that works, we imagine, is that this input goes through some function, say such as this, so that the greater the input, the greater the output of the unit, goes through some function to compute a number. Real neurons have a maximum rate of firing that they take on, and we assume that ours take on some maximum. They also have a minimum, namely not firing at all. So we have, so this is what we think an individual unit does in our model systems. And we're going to try to get units like that to behave in an intelligent way. How can we possibly do that? These are pretty dumb units. All they can do is sum up numbers and give out a number through a very simple, and moreover, in most of our models, they're very homogeneous, very simple. All units essentially sum up numbers in the same way, and they produce numbers in the same way. So how can we make these do interesting things? Well, it turns out, to a first approximation, all the knowledge in the system, such as this, is all encoded in the pattern of interconnections. Depending if unit A connects to unit B or not, that fully determines the kind of computation that the system can do. And not only do they get to connect, but they get to connect with some strength. Listed here, well, I have omegas there, I guess, to represent the strength of connection. Now, how do we store information in a system like this? How do we get it to compute something in particular? Well, the answer is by setting up a particular pattern of interconnections and a particular pattern of connection strengths, It turns out that we can we can compute arbitrary functions that way by having patterns and sequences of such interconnections. And so the trick is, one trick is, to figure out what pattern of connections it is that makes a whole network of these things compute in a certain way. And how can we discover, or how can we know, how can we program this device? Notice that programming this kind of a computer more or less means stating what the pattern of interconnections are and what the strengths of those interconnections are. Note that the strengths are numbers. They can be either positive or negative. If they're positive, that means that activity from this unit, say if this is positive, activity from this unit increases the net activity of this unit. If they're negative, it's inhibitory and it decreases it. That's the machinery that we get to work with. To a first approximation, it's a very highly oversimplified view, but to a first approximation, that's the kind of abstract system that we're going to imagine that brains are. And what we're going to try to do is talk about how can we get systems like this to do interesting computations. How can we get systems like this to show an emergent intelligence? And that's the game. Now, you might think that it's impossible or very difficult, but it turns out it isn't. It turns out that a lot is known about systems like this. Well, let me just say, you can imagine if you have an arbitrarily interconnected set of these things that are all feeding into one another in arbitrary ways, what we have is essentially a kind of nonlinear dynamical system. We have a system that goes through a set of states and passes through, and it has all the behavior, it can have all the behavior of any nonlinear dynamical system. We put inputs into the system, we perturb, that is, the external world somehow perturbs some of those units. It adds activity to some of them. In so doing, then, it perturbs the network, it perturbs this dynamical system, and if it perturbs it in appropriate ways, it pushes it through certain patterns. And programming a system like this is a matter of setting it up so that when it's perturbed in a certain way, it will flow through a certain set of states or certain sets of state descriptions. So that's the idea. Now, it turns out that there are a number of features that these kinds of systems have, and let me just go through a few of them here. In fact, most of the rest of the time I'm going to spend just going through these different characteristics and showing how these kinds of systems can have those kinds of characteristics. First of all, these are self-evidently parallel systems. They're parallel in that every unit is working independently of every other unit in the whole system. And we know that we're getting rather close to the limits of how fast single CPU systems can go. We're running into some physical limitations on the speed. And if we're going to continue to do better and better, more and more processing for less and less money and the like, it's clear that we're going to have to go to parallel systems. And the problems, of course, as any of you who thought about this know, that it's very hard to program parallel systems. This is sort of one of the major problems of parallel computation. And here, then, what we have is a system which is parallel, which is capable, we think, of doing interesting computations. What kinds? One kind of computation that it can do that's very common in artificial intelligence is constraint satisfaction. Namely, suppose that we have a set of constraints, and what we would like to do is find a solution which optimally meets as many constraints as possible. In fact, we can make it more general. We can imagine that each constraint has a certain importance associated with it. And what we'd like to do is find a system which maximizes as many of these constraints as possible and makes the total system maximally consistent. This is a very common task, I think, in AI. And it's an interesting kind of programming, by the way. Rather than programming it via a specific algorithm to solve a particular problem, we program systems like this by stating a set of constraints on the solution and let the system discover the solution that best meets the constraints. It's a different kind, it's a very general purpose computational algorithm if we have this kind of thing. And I claim that these systems solve these kinds of problems in rather nice ways. Now let me give a very quick example, since I'm obviously going slower than I should here, of a kind of constraint satisfaction system. This will take a second, but if you look down here, what you're supposed to see is a Necker cube. A Necker cube is one of those devices which essentially a two-dimensional drawing, which can be seen as a three-dimensional cube, as one of two three-dimensional cubes. In one view of it, this is the front face here, and it's going back like this. In this another view you can get, this is the front face up here, and it's sort of going back. So the front face can be pointing, let's say, to the lower left or to the upper right. Okay? Everyone can see those two alternative readings of the Necker cube. Now, what I'm going to show is a way of building a computational device that can settle on what we'll call an interpretation of this Necker cube by satisfying a set of simultaneous constraints. Turns out that the network that we build in this case is essentially bistable. That is to say, it has two states that it can fall into easily, and those two states correspond to, as it turns out, the two interpretations of the Necker cube. So here's just to give you the idea of how each unit in this network up here, these are units of the kind I was talking about, each unit corresponds to a hypothesis about the external world. So this one, for example, FLL, front lower left, corresponds to the hypothesis that this vertex is a front lower left vertex of a cube. This here, BLL, stands for the hypothesis that it's a back lower left. Now, since those two are inconsistent, that is, it's either front or back, not both, we have a connection which represents the constraint, namely that both of these can't be on at once. And those little balls mean it's inhibitory. So when one's on, it tries to turn the other one off, and vice versa. Now, similarly, this one, if we look, see, how can I do that? If we look at the left-hand side, as you're looking at it, you can see there are 8 little circles, and those correspond to each of the 8 vertices. And on the right-hand side, there are 8 circles. Now, what will happen is if all these are on, then that'll correspond to the view that this is the front face. If all these are on, that corresponds to the view that this is the front face. So we have alternative inconsistent units are negatively connected to one another. Units that are consistent locally are positively connected. Those are the arrowheads. So if this is front lower left, then this would be front lower right. So they're positively connected to one another. So when this goes on, it tries to turn that one on. Now what will happen? Suppose by chance or some other way, one or two of these units were turned on. What happens? That's the outside world perturbing this dynamical system. What happens? It tends to try to turn its neighbors on and turn off those guys that are inconsistent with it. And what happens in this case is that it settles rather directly into one of two states. Either the state in which the left-hand units are all on, corresponding to one interpretation, or the right. What we've done is translated a problem, in this case in perception, into a constraint satisfaction system, which says that the constraints are of the form, if when one element is on we want the other one on, we put positive connections. If they're inconsistent, we put negative ones. That's the way we're going to characterize this. Now, in general, it can be shown that under appropriate conditions, the system will find an optimal, this one happens to have two, but will find an optimal interpretation. That is to say, it will find a set of constraints, that is, it will find a state, a pattern of ons and offs for the units, such that the maximum number of constraints are satisfied. That is to say, what it really does is, you can imagine it sums, if both of these are on and they have a connection of some strength S, then that contributes to their goodness, if it's positive. If it's negative, it subtracts from their goodness. And what we can do then is sum up all the goodnesses over all the pairwise connections, and the system will, in fact, you can show under fairly a variety of conditions, the system will in fact come to an optimal. That is, it will turn on as many as it can and off as many as it can in order to get that number, that sum, as big as possible. All right, so that's constraint satisfaction. Now it turns out that this constraint satisfaction mechanism lies behind a lot of what these models can do, though not everything. So an important thing they do is constraint satisfaction. Second kind of thing they do nicely is what we might call interactive processing. That is to say, every unit speaks a particular language. That is to say, it sends out activation. And any other unit in the whole system can understand that activation as if I get some input, I should either increase or decrease depending on whether the connection is positive or negative. That means that units that are associated, let's say, with low-level vision can communicate in a natural way with units that are associated with, let's say, language processing. Whereas, because the nature of the data structures and data flow within these systems doesn't require that we sort of segregate them from one another, it rather says any unit can interact with any other unit. It doesn't have to know about the kind of representation that it is, because they all speak the same language, namely activation flow. So the homogeneity buys us the ability to succinctly organize, actually, I call it interactive because what I mean is the different modules in the system are all able to fully interact with one another. There is no necessity to do, well, in fact, there's no necessity for what might be called modular programming in systems like this. It's entirely interactive programming, or can be. A second kind of thing, or a third rather, fourth I guess, is that these systems are good at are rapid pattern matching, best matched search, and content addressable memory. How does that work? Well, it works essentially in the same way that the previous systems worked. Namely, what we can do is store information in the network. We can then use part of that information. We can do a content addressable memory. We can use part of that information as a probe to the network. We can then allow the network to settle into a state which is maximally consistent with that probe. That's the sense in which it's doing content addressable memory. That is to say, we can take, if we have a pattern, we can take part of it as a, if you will, a clue or a probe into the memory, and then it will bring back the missing parts, so to speak. This is a fairly common, just to give a simple idea about how memories like this can work, I'll give you the very simplest version. How do we store information in networks like this? Information is in the pattern of interconnections. We can imagine that this whole network corresponds to a memory. In fact, it's a memory/processing system. In this case, it's a fully interconnected network. Everything connects to everything else, though that's not necessary for these systems to work, but it's convenient for this description. We imagine that the outside world impinges on some subset, perhaps all, of these units, and that there's a pattern corresponding to a level of activity along each input line. What we'd like to do is store that pattern and then be able to retrieve it. How do we store it? we can think of it as like a word. If these were 0 and 1, it'd be like bits. In this case, we'd have a 3-bit memory, but we could have millions if we wanted. Now, how do we store information? In general, we think of these as real numbers, however, though they could be binary. Well, roughly speaking, the simplest learning procedure, the simplest way of storing information in these networks is the following. If we have a pattern of activity coming in from the outside world, if this unit is on and that unit is on, then we should strengthen the connections between them. And essentially what we do is we strengthen the connections by the product of the activities of those two units. That's what's called the Hebbian learning procedure. After the neurobiologist Donald Hebb, who first proposed this, what that does is it strengthens these connections, and if this is on and that one's off, then we want to weaken those connections. So what does a memory look like? Notice this is what we call a distributed memory. It's distributed in the sense that every memory that we store in this network involves the same subset of units, or the same set of units. So all memories are stored in the same units. And every unit participates in every memory, and every memory involves all the units. That's fully distributed memory. And what does a memory trace look like? Gee, a memory in this system is just a modification of the strength of connections. And we simply add them all together, one on top of the other on top of the other. So we get a superpositional memory in this system. And how does retrieval work? The way retrieval works is that we turn on some subset of these units, and we allow the system to then go through a state of interacting until it settles into some state. And if the connection, as this learning rule has symmetric connections, if the system has symmetric connections, then it will actually settle into a state. Eventually it'll go to a point attractor in the state. It'll settle at a point, and that point will be ideally the state which maximally is consistent with the connection, the unit, the things that you actually turned on. Now there might be more than one that's equally good, and depending on exact details of it, it may select one of those equally good ones, or it could get one that's not quite as close under, it may not find the global minimum, it may only find a locally best solution. But in any case, what we have then is a memory. Now memories like this have a number of interesting properties that make them intriguing. And here are a set of these properties. First, when a known signal, that is one we've stored in the way that I just mentioned, when a known signal is presented, the system responds by amplifying the signal. What we have is a signal which matches a set of changes that were once made in the system, and what it will do is tend to amplify that signal. You can think about this as some sort of familiarity response, if you like. If you have an unknown signal, that is one that wasn't presented before, then the system essentially damps it down, turns down the signal. Why? Because on average half of the strengths are positive and half of them are negative, and if they're sort of completely uncorrelated with these inputs, they'll cancel each other out, and the signal will actually damp down. When part of a known signal is presented, the system can respond by filling in the missing parts of the signal. This is sort of the reconstructive property. When a signal similar to a known signal is presented, the system responds by distorting the presented signal toward the known signal. It has a property of sort of assimilation. It tends to respond similarly to similar signals. That turns out, as I'll say in a few minutes, to be an important feature. Finally, when a number of similar signals have been stored, the system will respond strongly to the central tendency of those signals, whether or not it's been presented itself. Now this is a nice feature. Oh, I should say that it was these features that first got me interested in these systems. These correspond rather nicely to the way human memories work. And in a rather weak way, I think, to the way in which, at least the simplest ways, in which we can organize memories in symbol processing systems. So this ability to do prototypes, respond to similar things, find best matches naturally, and so on, those are all features that seem to be characteristic of human memories. Okay, so this is the kind of mechanism then that we can use to do rapid pattern matching. That is, we put in part of the pattern. In parallel, it will find the best match. That is, it'll find the state which is best matches, best satisfies the constraints coming from the outside world in this case, and its internal constraints stored in the connections, and a content addressable memory. Another important point is that it does automatic generalization and direct representation of similarity. That is to say, if two patterns are similar, that is to say, many of the same units are turned on to the same degree, then the network treats them in similar ways, even though it's never seen it before. And so it will generalize. It essentially generalizes via a mechanism that we might call interpolation. That is to say, it responds more or less to an item more or less halfway between the way it responds to two close neighbors. It more or less does interpolation, which sometimes is the right thing to do and sometimes is the wrong thing to do. But you can't, in order to overcome this, we have to do other things than the kind of learning mechanism. We have to have more sophisticated learning mechanisms than the one that I've talked about. Another feature, let me just mention here, before going to learning, which is what I'll spend the last 10 minutes on. Another feature is a feature of graceful degradation. Graceful degradation is the characteristic of these systems of being rather, how should I say it? We have many, many units, all interconnected. Any given connection, or any given unit for that matter, doesn't play a very important part in the performance of the system. If you damage the system, what happens is you get what we call graceful degradation. That is to say, it just gets a little worse. Everything, there is no sort of linchpin. And for actually this feature, plus its adaptability, make it rather interesting, say in the world of building hardware. Say you want to build a computer, wouldn't it be nice if the computer didn't matter too much if some of the parts weren't working? Conventional computers that we're used to, by and large, have quite a few parts that are linchpins. If they're not working, the system breaks, goes down, it won't work. Whereas in these systems, essentially no part is essential. The system will, and if we have learning, the system can even learn around missing parts so as to perform just as well as it did before once it's had some training, or almost as well. Okay. Now, the last point, the rest of the time, I want to talk about learning. These systems, one thing you can see, if you have this kind of a computer, programming it is a big problem. Going in there and specifying what all those connections should be is very hard to do, essentially impossible for complex things. Getting it, I'll assure you, having tried to build some of these by just figuring out what the connection should be, I'm usually wrong. That is to say, in complex, nonlinear dynamical systems, it's very hard to predict exactly what they're going to do. We need adaptive systems. We need systems which we program not by giving them the algorithm, but by giving them some examples. So we program extensionally. We give them examples of what they're supposed to do, and then we want the system to be able somehow to adapt to an environment in which it behaves that way, in which it does it. And it turns out that one of the nicest things about these kinds of systems is that because they're so homogeneous, every unit is essentially the same, we can get very simple, homogeneous learning procedures which allow them to adapt to new systems, to new environments, to new inputs in a fairly powerful way. And let me talk briefly about some of those. Essentially, the idea is we have this network, it's performing in some way, and we want to shape it. We want it to do what we want it to do, not what it wants to do. And how do we shape it? Well, we shape it by giving it information about, somehow giving it feedback that its performance isn't up to snuff. It's not doing what we want it to do. Now, the interesting thing is that what we're interested in is the behavior of the whole network of these units. We're not interested in the behavior of any given one unit in the system. We're not interested in shaping it up particularly. We're interested in shaping up the overall behavior of this network. So it computes the right function. When we put a particular input, we want a particular output. We don't want it to do it wrong. So how do we do that? Well, one thing we can do, and there's a long sort of tradition here, goes like this. We can imagine the simplest of networks. Simple network in which we have a layer of inputs and a layer of outputs, and we want it to compute a desired function. In this case, we can imagine this to be a map from a vector input to a vector output. A set of numbers. That's all we want it to do. How do we accomplish that? Well, we can put a vector in and a vector out, and then we can say, gee, to what degree does that vector that it produced, to what degree is that what it should have produced in this case? And we compute an error. We can look at the difference, component by component, between what it actually produced and what it was supposed to produce. And based on that error, then, we can change these connections so that next time it will do a better job. And if we do this repeatedly, this kind of a network will eventually get so that it will do as good a job as it can, in the sense that it will reduce that error as much as possible. It will reduce the error as much as it can, but it may not actually completely solve the problem. Indeed, we can show a number of cases where this kind of a network is insufficient. It won't solve the problem. And the reason is roughly this. Similar inputs must go to similar outputs to a first approximation. And the world isn't always organized so nicely as that. Sometimes the world is organized in such a way that we want similar inputs to go to different outputs. Take, for example, a lowercase a, which is pretty similar to a lowercase o, much more than it is, say, to an uppercase a. We would like it to be able to make that discrimination. Perhaps it wouldn't be able to with this sort of system, but it turns out that if we complicate the system just a little, namely, if we have inputs, map them onto a set of internal representations, that is, do two mappings, then we can essentially map sort of arbitrary vector functions onto, we can compute essentially arbitrary vector functions in this case. If we have a separate layer here. But the problem of this is, we know there's actually quite a simple rule that allows us to learn in the one layer case. We need a case, and that one is essentially a matter of trying to simply minimize the error function in a standard way. And what we need to do is generalize that to a multi-layer case. And I'm not going to have time to describe this in any detail, but let me just tell you about it. Essentially, the idea is this. We start with a global function of error. This tells what's we present the system with an input, we look at its output, and see how it differs from the target. And we can get a single number here called E, which is the sum of the difference between the target minus the actual output squared, summed over the whole vector. In fact, summed over the whole vector. And what we would like to do is find out how, if at all, we can change a connection strength so as to reduce the error. And we'd like to be able to change a connection strength anywhere in the whole network. This is a kind of a credit assignment problem. What we've got, imagine a gigantic network and you are a unit in the very middle. Something came by, you did something. Later on, the network performs in a bad way somehow. How do you know that what you should have done different? I mean, maybe you were off when you should have been on, maybe you were on when you should have been off. Maybe you did just the right thing. How do you know? That's the credit assignment problem. This procedure, so-called what we call here the generalized delta rule or backpropagation learning, is a mechanism for assigning credit to any unit in a large network. And essentially, the idea of it is that we're going to try to reduce this problem to the problem of finding minima in error functions. That's what we're looking for. We want to get the system to perform as well as possible. That's a function minimization task. That's all it really amounts to. In general, we can imagine plotting for a particular weight in the system the error function as a function of this weight. Now, nobody is ever going to actually plot this, but conceptually, we have that kind of a system. Now, what can we do? Well, what we can do is essentially what's called gradient descent. That is to say, if we can compute the derivative of this error function with respect to any particular connection in the system, then we'll know how to find the minimum of this function. Namely, if the derivative is positive, we should reduce the weight, reduce the connection. If it's negative, we should increase it. And if we do this, eventually we'll find a place where the derivative is 0. And we're doing this simultaneously, though, to all the connections in the whole network. Now, I'm not going to bother you with the math here, just to say that it turns out that if you have units of the kind that I described, then we can have a system which is capable of actually adjusting itself, adjusting all the connections in the whole system, so as to be able to perform as well as possible these kinds of mappings that I was talking about. And in order to do this, essentially what it's doing is learning a kind of internal representation. That is, two layers or many layers of code. It doesn't matter how complicated the network is. It can even come back on itself. And we still know how. It's just through the how should I say it, virtues of the chain rule. We know a very simple way of doing this. And let me just show you what the result is, more or less. You can imagine a network, for the moment imagine a layered network, arbitrarily many. If at some point in time, and this is going to be a recursive, if at some point in time we get a measure of error called delta associated with a set of units, then we can compute a measure of error for any other unit by doing the following. This guy is a credit assignment problem. He wants to say, how much of this guy's error is due to me? How much of him? How much of him? I'm just going to add them all up. And that's going to be my error measure, my delta. And the rule turns out, when you do the math, to say that we should multiply his error times the strength of connection from this guy to this guy, and add that to this and so on. We get this nice little sum here. And then we change this connection in proportion to the product of the error measure times the activity on this unit. And that just comes out of the math. Once we do that, you can see we can pass that error all the way down, where a unit can, entirely locally, only needs to know the other units to which it's directly connected. It only has to communicate with those. Now, it turns out, and I'm not going to have a chance to really show you any further examples of the application of this, but it turns out in a very simple network, for example, of the kind that I showed you, it's possible, for example, for a system to learn to map from the letters embedded in words in English to the relevant phonemes. So, for example, oops, can't write on that. For example, take the word like the A in cake versus the A in cat. In cake, it's pronounced A, and in cat, it's pronounced A. And we can find a system that's capable of looking at build a system that's capable of learning. Essentially what we do is, Terry Sinofsky and at Johns Hopkins applied this learning procedure to a thing he called net talk, which he presented the system with words and taught it essentially to compute the function of giving the correct phonetic output for the particular word. So all he needed were pairs of spelled words and phonetic output. He could take those pairs and just present it in an extensional way, give it examples, and then it could learn to do this mapping. Once it learned to do this mapping on, let's say, 1,000 words or so, was able to generalize to other words in the dictionary. It was able to do this in a way which involved not the typical intentional programming, that is, telling it how to do it, telling it what the algorithm is. Gee, if you see an A, check to see if it's got a final silent E or whatever. But rather it learns to do it essentially through induction, through simply giving it examples. It's learning the general principles of spelling to sound communication, mapping, and then able to apply that function to novel cases that it's never seen before. Well, that's just one example. There are many, but I think I should stop.
Before we have questions, let me mention something I forgot to mention in the introduction. Dave Rumelhart is a senior editor of a couple of volumes dealing with these kinds of issues. And so how can we find out more, Dave? Okay,
I'll tell you. The group of us at San Diego that have been working on these for the last 9 or 10 years put together a series of 2 volumes, soon to be a 3rd actually, which are called, it's published by MIT Press, and it's called Parallel Distributed Processing, which is our general name for this class of system, subtitled Explorations in the Microstructure of Cognition. And we have 2 volumes out. They may be in your bookstore. I haven't checked, but I know they have been in the past.
Do you see the audience for questions?
Yes.
This is sort of an unfair question to ask since these systems are still in their infancy, but these sorts of systems seem very good at doing gradual approach, sort of relaxing down onto the right answer for something. Mm-hmm. But there's substantial evidence that humans and a lot of animals can do one-trial learning. So you get radical changes in learning and behavior within mm-hmm. one trial. And how in general would you see these systems as accounting for that kind of thing?
Well, let me just be clear about one-trial learning. There's no problem in having these systems do one-trial learning. And I'll explain how in just a second. The problem is the degree to which you know it forever, given that you've heard it for one trial. And let me just explain. Clearly, one can always do the following. You can present a pattern to the system for several times, iteratively, the same pattern, and it'll be able to respond to that appropriately. Now, what will happen, though, is if you then present other patterns over a period of time, it will degrade your knowledge of the thing that you'll get interference effects. It'll degrade the knowledge that you taught it before, and next time when you test it, it'll show a savings. It'll be better than if you'd never taught it before, but essentially you'll have to tell it again. And so in fact, it's not so difficult to get it to store a pattern one at a time, but that's not actually the most efficient way of learning general whole set of patterns. Most efficient way is not to present each one until it knows it perfectly, or should I say hold it on until it knows it, but rather to intersperse them, because that gives it information about what the whole ensemble is that it has to learn. So usually in our learning experiments we don't do the former, that is, learn each one, but rather we learn them just a little bit, just a little bit, just a little bit. Give it a sample of the whole environment so that it then can learn more efficiently and more quickly.
What do you see as being the main problem? Here's microphone.
Yeah, what do you see as being the main problems that need to be solved in PDP approach?
Well, I can tell you the things that I intend to be working on, which were chosen in part because they seemed like important problems. One issue has to do with what you might call higher level reasoning. I'm interested in working on things, trying to give an account of how people can do logic, how they can do mathematics, and so on, which are things which seem rather foreign at first blush to these kinds of systems. I believe that there are a number of features of these systems that will allow them to behave more like people in the face of these sorts of things. One area I think that's important is in the case of, let's say, analogical reasoning, something which I think these systems are going to turn out to be rather well suited for. Indeed, I've done some work on this. But in any case, I see the whole issue of, somehow when you turn the thing on its head, it's been more traditional, let's say in AI, to start out with logic as your prime thing, and so doing logic was never a problem because that was the basis of it. Whereas in this case, we've more or less turned it on its head. We've said, no, logic isn't the center of this sort of a computational system. So then you can say, how then do people do logic? Well, my answer to that in partly is not very well, but nevertheless they can learn to do it. And how is that accomplished by these kind of systems? So that's one question. Another question has to do, that's even more difficult perhaps, but I also don't think impossible. And that is, how do we deal with essentially highly structured entities, like let's say sentences or pieces of discourse and so on, which are highly structured pieces of data, which in principle are, for example, unbound. People will say, gee, sentences are unbound. There's no finite length how long a sentence should be. Not that we find sentences of arbitrary length. That is, the longest you usually find are maybe 100, 120 words, or about as long a sentence as people ever say. But nevertheless, the issue is that you don't want any a priori restrictions of this kind. How do you deal with those kinds of things? So those are two central problems.
There's one more short question.
Yeah, sorry.
How do you conceptualize individual differences between brains or minds of people? What you presented now is a generic system that
Right.
should work for everybody, but we know there are individual characteristics,
Right.
something like personality, or whatever those are.
Well, there are a couple of things to be said about that, I think. First, of course, even if we start out perfectly homogeneous, which I don't believe, but even if we did, every system would have since it learns from its environment, adapts to its environment, the degree to which there are differences, perhaps whatever, in the environments, we will find the systems to actually learn different things. In the case of NetTalk, it's rather interesting. If you give it, typically we start these things out in some fairly uniform random state. But what we find is that each time it actually learns to do the task, but if we look at the detailed structure, it's rather different. And that leads to slightly different kinds of mistakes that it makes when it makes errors. So there's a natural, in a learning system, the environment itself, since it's not constant for every case, is a natural source of heterogeneity. Also, of course, depending on exactly, the system has various parameters. It begins with a various pattern of interconnections, and those could correspond to more what you might think of as, let's call it genetic differences between these, or a priori differences. So both of those are sources here, as I think they are in people.